Welcome to a journey of enlightenment where we unravel the mysteries of solar panel energy consumption. Join us as we explore the silent symphony of solar cells, the dance of photons, and the harmonious balance of sustainability and innovation. From the bustling cities to the serene countryside, solar energy touches lives, powers dreams, and promises a future bright with possibility. Stay tuned as we delve into the technical marvels, environmental impacts, and inspiring stories of solar power. Let's illuminate the path to a cleaner world, one ray of sunshine at a time. Imagine a world where every rooftop, every surface becomes a silent generator of a clean, inexhaustible resource. This is the world of solar energy, a realm where the sun's embrace is transformed into a power that fuels our lives. In the heart of a bustling city, a young entrepreneur marvels at the simplicity of the panels above. It's like capturing a piece of the sun, she muses, her thoughts a reflection of wonder and ambition. As the day unfolds, a scientist in a distant lab pores over data, a smile playing on his lips. The photons, he explains to an eager intern, they're the messengers of energy, and we've learned to listen. Elsewhere, a family gathers around the dinner table, their home aglow with the day's harvest of light. To think the patriarch reflects the power of the stars now harnessed for our hearth. The narrative weaves through the lives of these individuals, each a testament to the silent revolution unfolding above. A teacher, standing before a class of wide-eyed students, speaks of capacitors and storage, her words painting a future bright with possibility. In the quiet of the evening, a poet's voice whispers, the stored sun sings of warmth and light. The tale culminates in a vision of harmony, where the mysteries of solar panel energy consumption are not just unraveled but embraced as a beacon of hope. Now let's delve into the technical aspects of solar panels. In the bustling heart of innovation, solar panels, or photovoltaic PV systems, are marvels of engineering, capturing the sun's energy and converting it into electricity. A researcher whose life's work is to unravel the intricacies of these devices. Solar cells, she continues, are typically made from silicon, a material that excels at converting light into electrical energy through the photovoltaic effect. The room listens intently as she describes how photons from sunlight strike the solar cells, liberating electrons and generating a flow of electricity. A nearby technician interjects, each individual cell is a quiet powerhouse, producing maybe around 1 or 2 watts. However, when we connect them in rows, they merge into modules, and subsequently, they combine to form larger sets, growing the energy output to power anything from a basic calculator to a sprawling city. His hands move effortlessly over a control panel, an intricate dance of attention to detail and care. An engineer from across the room interjects, while we don't forget the importance of the inverters. They are the unsung heroes that transform direct current DC power from the solar panels into alternating current AC, the electrical form we use annually in our homes and businesses. The crowd nods their heads, comprehending the significance of this pivotal change. Solar panels aren't merely collectors of light. They are architects of a future where energy remains clean and plentiful. Filled with layers of silicon, phosphorus, and boron, these dynamic solar panels stand at the forefront of a groundbreaking energy revolution. She contends, solar tracking systems play an essential role in maximizing the efficiency of solar panels by ensuring they consistently face the sun. Let's delve deeper into how these systems work, the variety of their types, and their advantages and disadvantages. Are you curious about how solar tracking systems work? Solar trackers enable panels to keep a consistent angle with the sun's rays, maximizing sunlight exposure. Through the use of devices such as adjusters and sensors, they may adjust the orientation of solar panels in order to match the sun's position throughout the day. This precise alignment significantly enhances energy production. A typical solar tracker incorporates several key components. 1. Tracker mount. This component supports the panel in the correct angled position. 2. Driver. This device manages the rotation of the motor shaft. 3. Sensors. These devices help determine parameters influenced by the sun and provide precise output. 4. Motor. This component manages the tracker's movement. 5. Algorithm. This device calculates the sun's position by means of dates, time, and the location. 6. Working principle. When sunlight intensity increases, the panel operates and sends data to the sensors. The data is then transmitted to the programmable logic controller (PLC), which generates an output to turn the motor, driving the panel to match the sun. A solar panel perfectly aligned to the sun creates more energy output than one that is at a less optimal angle. The types of solar trackers include single-axis trackers. These trackers rotate on an east-west axis, enhancing solar absorption by 25% to 35%. They increase efficiency, reducing the payback time for installation costs. Dual-axis trackers, rotating on both a north-south and east-west axis, these trackers maximize energy output by up to 45% compared to fixed-tilt systems. Are you aware of the benefits and challenges of using solar trackers? Solar trackers can increase panel efficiency by up to 10% to 45% and reduce the payback time for installation costs. Ideal for large-scale projects, their efficiency in capturing sunlight makes them beneficial for ground-mounted solar panels. However, the challenge is their cost, complexity, and potential maintenance needs. Roof-only trackers rotate and align solar panels using a fixed or adjustable mechanism, reducing initial setup costs. Maintenance. Moving parts may require maintenance over time. In summary, solar tracking systems are crucial in enhancing the efficiency of solar panels. By dynamically adjusting their position to face the sun, these systems effectively maximize energy output, contributing to a cleaner and more sustainable energy future. Stop. Consider the efficiency and degradation over time. Solar panel efficiency and degradation over time are vital factors to consider when evaluating the long-term performance of a solar energy system. Here's an overview. Efficiency over time. Solar panels are rated based on their efficiency at converting sunlight into electricity. The efficiency of a solar panel is determined by the amount of energy produced per unit of surface area. Higher energy output signifies greater efficiency. The peak efficiency of solar cells can reach up to 39.5% for triple-junction solar cells. However, multi-junction concentrator solar cells achieve as high as 47.1%. Degradation. Over time, solar panels experience a natural decline in efficiency known as degradation. This is due to exposure to ultraviolet rays, adverse weather conditions, and wear and tear of materials. The average degradation rate for solar panels is about 0.5% to 1% per year. After 20 to 25 years, your solar panels may operate at roughly 80% to 90% of their original efficiency. Factors affecting degradation. Light-induced degradation (LID). Efficiency is temporarily reduced at the initial exposure to sunlight due to the motion of boron and oxygen within the solar cells. Potential-induced degradation (PID). Loss of performance caused by the flow of current between cells and other components. In conclusion, solar tracking systems enhance solar panel efficiency by adjusting position to face the sun, maximizing energy output for a sustainable, renewable energy future. Aging. Over the years of continuous operation, solar panels experience a decrease in performance due to various environmental variables and sustained thermal stress. Backsheet failure. The discoloration or even the complete delamination of the protective backsheet layer can lead to considerable degradation of the solar panel's performance. Calculating efficiency. The efficiency of a solar panel can be accurately calculated using the following formula. Efficiency percentage is calculated by deciding a maximum power area in square meters and multiplying it by 100%. Efficiency percent equals area maximum power 1000 times 1099. Now, allow me to emphasize the significant environmental impact of solar energy. Positive environmental impact, reduction of greenhouse gases. Solar energy systems do not produce air pollution or greenhouse gases during their operation, which can significantly minimize the carbon footprint on both local and global levels. Sustainable and clean, the sun provides an incredible resource for generating clean and renewable electricity without the generation of toxic pollution or the emission of global warming gases. Energy independence. Utilizing solar energy promotes energy independence and can have a positive, indirect effect on the environment when it reduces or replaces the use of other energy sources with much larger environmental impacts. Challenges and considerations. Land use. Depending on their specific location and design, larger utility-scale solar facilities can raise concerns about land degradation and habitat loss. Water use. While solar PV cells do not require water for generating electricity, the manufacturing process and certain types of solar power plants may require significant amounts of water. Hazardous materials. The production of solar panels involves a variety of materials that may be energy-intensive to acquire and may also use hazardous chemicals that need careful handling to avoid environmental contamination. Life cycle and recycling. Energy payback. Solar panels can produce energy equivalent to the energy used for their manufacture within 1 to 4 years, and most systems have operating lives of up to 30 years or more. End-of-life management. Efforts are being made to address end-of-life issues related to solar energy technologies, including resolving disposal and recycling problems related to PV cells and panels. Innovative solutions. Integrating with agriculture. Installing solar energy systems on land with marginal agricultural value or integrating them on farms may provide economic and environmental benefits. Minimizing water use. Technologies like dry cooling can reduce water use at solar power plants by approximately 90%, though there are trade-offs in terms of cost and efficiency. Solar energy's positive environmental impact, along with optimal expansion, reduces dependency on fossil fuels and minimizes harm. Here are some examples of successful solar energy projects from around the world that showcase the potential and impact of solar power. Eunice Solar Project, Texas, USA. This project is one of the largest in the U.S. with a capacity of 420 megawatts. It's a significant contributor to the country's solar capacity and demonstrates the scalability of solar energy. Cochin International Airport, India. This airport became the world's first fully solar-powered airport, setting an example for sustainable transportation and infrastructure. It has a significant solar plant that powers all its operational functions. Benben Solar Park, Egypt. As one of the largest solar parks in the world, Benben has a total capacity of 1.5 gigawatts. It plays a crucial role in Egypt's renewable energy strategy and provides thousands of jobs. Adelaide's Tindo Solar Bus, Australia. The world's first solar-powered bus, Tindo, operates in Adelaide and is recharged using 100% solar energy, representing a pioneering step in sustainable public transportation. Rancho Seco Solar to Project, California, USA, built on the site of a decommissioned nuclear power plant. This 160 megawatts project has a 30-year power purchase agreement with the Sacramento Municipal Utility District, showcasing innovative use of land and resources. Lac des Toules Floating Solar Farm, Switzerland. Positioned high in the Swiss Alps, this floating solar farm benefits from strong solar radiation and the albedo effect, producing 50% more power than lower-altitude plants. These projects illustrate the diverse applications of solar energy, from powering airports to public transportation, and from large-scale solar parks to innovative floating farms. They highlight the versatility and environmental benefits of solar power, contributing to a more sustainable and cleaner energy future. As our exploration comes to a close, we stand in awe of the sun's boundless energy and the ingenuity that harnesses it. We've journeyed through the technical depths, witnessed the environmental benefits, and celebrated the success stories of solar energy. Remember, each panel is a pledge for a greener tomorrow, and every photon captured is a step towards a sustainable legacy. Thank you for joining us on this enlightening adventure. May the power of the sun continue to inspire and energize our world. Until next time, keep shining on.